Alice loans Bob $500, and they agree to 10% interest compounded once per year. Suppose Bob never repays his loan to Alice. So we're going to set up a little table. And of course, at year number 0, Bob owes $500, because that's how much money he borrowed. After 1 year has passed, how much money does Bob owe Alice? Yeah. He owes her the original $500 plus an additional 10% of $500. And 10% means 10 divided by 100, which is 0.1. In fact, the word percent comes from Latin. Per means divide by, and cent means 100. So, see, percent means divide by. 10% is 0.1. And that means that at year number 1, Bob owes Alice. And you know, you can always factor out the 500 too. I want to point this out. It'll be useful later. This would be 500 times 1 plus 0.1. It would be 500 times 1.1, and that's 550. Do I remember to hit record? Yeah, I did. Okay. In year 2, how much is Bob going to owe Alice? He's going to owe her the original $550 from year 1, right? Plus 10% of $550. In other words, this is factor out the $550. 550 times 1 plus 0.1, so 550 times 1.1. But 550 was just 500 times 1.1, and so this is actually the same thing as 500 times 1.1 times 1.1. And in any case, this is going to be 550 plus 55, that's $605. What about at the end of year 3? Well, Bob is going to owe $605 plus 1/10 of $605. And that is going to be 605 plus 60.5. That'll be a total of $665.50. But I might also write that this is the same thing as 605 times 1.1, which I can get if I just factor out the 605, and I would just be left with 1 plus 0.1, and 1 plus 0.1 is 1.1. But $605 was just $500 times 1.1 squared, and so this would be the same thing as 500 times 1.1 cubed. So when I go to ask you, how much will Bob owe in 50 years? It would be a real pain, you know, it would take me all afternoon to sit here and keep on adding 10% of the previous year, and then 10% of the previous year, and then 10% of the previous year, and so on. But what I could do instead is just skip to this part, where I've already recognized the pattern. It'll be 500 times 1.1 raised to the power 50. So what is 500 times 1.1 raised to the power 50? This would be a test question where you want to have your TI-30 calculator ready so you can punch buttons. Definitely want to bring your calculator for the next test. anybody bring it today? You said 58,695? Okay. Yeah, so I'll trust you with that. I don't have any way of verifying it. I don't have my calculator today. If you have your TI-30 calculator, go ahead and pull it out and try plugging in the numbers to each of these questions, because sometimes it's easy to make little mistakes. But yeah, that looks like a lot of money. The reason for this is because we've got the amount we originally owed times some number that depends on the interest rate raised to the power of the number of years that have passed, right? In other words, my function is an exponential function where the variable is in the exponent. And you remember when we graphed exponential functions, they're pretty flat at first, and then all of a sudden they shoot up and get really steep as you go on to the right. That's the same idea here. If you were to graph this function, it doesn't grow that fast in the beginning, right? Going from year 0 to year 1, that was only plus $50. Year 1 to year 2, that was only plus $55. Year 2 to year 3, that was only plus $60.5. But this rate is going to continue to increase. It'll get larger, but it's also getting larger faster. That's what we mean by exponential growth. So these numbers get pretty big, pretty fast. Everything in the world is on a compound interest basis. So maybe you remember from school there was like a simple interest formula. And this would be totally wrong, but I'll show you an example that's just completely wrong, right? You might say, well, how much does Bob owe Alice? He owes the original $500 plus 10% interest per year for 50 years on $500, right? This is an example of what not to do. You might say, oh yeah, Bob only owes Alice $3,000, because that's $50 a year for 50 years, plus the original $500. But that is wrong. That is an example of what you might call the simple interest formula. That's some fairy tale that we tell to ninth graders, because in real life, nobody charges you simple interest. Every company, whether it's your bank, your credit card company, your home mortgage, your car payment, everybody uses compound interest. There is no such thing in real life as simple interest. Compound interest means at the end of every year, or every specific period of time, you stop and you add the interest to the principal. And then the next time you charge interest on the next amount. So notice I didn't continue to add 1/10 of 500. The second year I actually added 1/10 of 550 and then 1/10 of 605. And the next year would be 1/10 of $665. So that's what we call compound interest. We have a compound interest formula to make this easier to do. And I mean, you can read the formula right here. This is something to have memorized. M, the capital M, is what we call maturity value. The capital P is what we call principal. Principal is the initial dollar amount. That's before any time has passed. Maturity value, that's the dollar amount after some time has passed. The little lowercase r is your interest rate, but I'm going to always tell you what the interest rate is as a percent, because in real life people talk about interest rates as a percent. You might say, oh, my home mortgage has a 4% interest rate. But in this formula, you have to write that lowercase r as a decimal, not as a percent. N, the lowercase n in the formula, that's the number of times you're going to compound the interest every year. So if I say the words compounded annually, that means you compound 1 time per year, and n would be 1. If I say the words compounded monthly, like your credit card compounds interest monthly, that means n is equal to 12, because you're compounding 12 times per year, 12 months in a year. And then t is the number of years that have passed. So here's an easy question. Using this formula, we say, suppose you are 25 years old and you invest $1,000 in the stock market ETF. If that investment earns 7% interest compounded annually, what will it be worth when you are 65 years old? So if you see the words compounded annually, or compounded monthly, or compounded weekly, or compounded daily, or whatever, whenever you see compounded annually, I want you to immediately just write down this formula that you should have memorized. And then ask yourself, what am I trying to find? Am I trying to find M, P, R, N, or T? M. Yeah. It says, what will it be worth when you are 65? That means I'm trying to find the dollar amount after some time has passed. I'm trying to find the maturity value. If I'm looking for M, then every other letter should be given to me somewhere in the problem statement. So what is my P? 1,000. That's the initial dollar amount. What is my lowercase r?
0.07.
Yeah, perfect. So 0.07, because 7% means 7 divided by 100, or 0.07. So that's 1 plus r over n. What is n? 1, because that's compounded annually. That's 1 time per year. And then t is 40. Because if you invest when you're 25, and we're curious about the maturity value when you're 65, that means 40 years have passed. So we can simplify a little bit by hand and say this is going to be 1,000 times 1.07 raised to the power 40. So in your calculator, try it out if you brought your calculator to class. Only 1,497?
I don't think that's right.
That's not right.
Oh, I put 100 instead of 1,000.
Sorry, you said, yeah, $14,974? Cool. Okay. So, you invested $1,000, and at the end, you got out almost 15,000. I want you to know that these are actually very, very, very realistic numbers. Not the ages and the principal. But what I mean is, it would not be unusual for an investment to earn 7% interest. This is very realistic. And the cool part is if you really did this, you saved up $1,000 and invested it, this could be you, right? Like you could have $14,000 just about without ever having to work for it, without ever having to lift a finger. The only downside is you've got to be patient, right? You've got to be willing to put $1,000 away and then not touch it for 40 years. So that's kind of a big downside. But, this is the way that investments work. We'll talk more about interest rates here in a minute. But let's do another problem, another example. Suppose you borrow $1,000 in credit card debt. If that debt accrues 20% interest compounded monthly, how much will you owe in 5 years? Whenever I see compounded monthly, whenever I see those magic words, I immediately think of and write down this formula. And then I think, what is this question asking me for? M, P, R, N, or T? M. It's asking me how much will I owe after some time has passed. If it's a dollar amount after some time has passed, it's some maturity value, so I'm looking for M. Everything else should be given to me. So what is P? 1,000. Then what is lowercase r? 0.2. Yeah, because 20% is 20 divided by 100. That's 0.2. What's my lowercase n this time? 12. Because it's compounded monthly, it'll be compounded 12 times per year. And then raised to the power 12 times, what is t? 5 years. So, in your calculator, this is what you can type in. $1,000 times open parentheses 1 plus 0.2 divided by 12 close parentheses raised to the power open parentheses 12 times 5 close parentheses. I see students miss test questions a lot because they forget the parentheses. If you just typed in 1 plus 0.2 divided by 12 raised to the power 12 times 5, it'll give you the wrong answer. It'll do some other math, right? You need the parentheses to group things how they're supposed to be grouped. So, what maturity value do you get? Very good. My maturity value is $2,695. So if you buy something for $1,000 with a credit card and you just don't make any payments on it, that's equivalent to taking out a loan with a really crappy interest rate. If it's an investment, you're investing your money, you want the highest interest rate possible, but if you are taking out debt, then you actually want the lowest interest rate possible. And this is a very realistic number. Again, so if you were to Google search credit card interest rates, they'll tell you 20 or 21% for a credit card interest rate. That's not unusual. So that means if you're using a credit card, try to make sure you pay off that every single month or as fast as you can, because this stuff really gets out of hand, right? It's more than double 5 years later. So the other thing you'll notice is that whenever you go to invest money, you might only expect like 7% interest on your money. But if you try to borrow money, you're going to end up with an even higher interest rate. Kind of the cards are stacked against you a lot of the time, where you're not going to find a risk-free investment at 20% interest, and you're not going to be able to borrow money for anything less than like 8% most of the time. There are some exceptions. We'll talk about that in a minute. Now, there's another formula. This is called the continuously compounding interest formula. And this says M is equal to P times E raised to the power RT. That little lowercase e is Euler's number, so that's like 2.7. Notice this is pretty much the same as the previous formula, except I don't ever ask you what the compounding frequency is. You don't need to know how many times per year this interest rate is compounded. This formula is assuming a situation where you are going to compound the interest every 1 second or so, right? Just continuously sitting here compounding the interest. So there's not an n. Just assume that it's happening all the time. And this is the formula you get. And here's a little example. We're going to use this formula. I'll tell you why. Suppose Walmart has a market cap of $697.52 billion. If Walmart grows continuously, and this is the magic word where you see the word continuously, you immediately write down this formula. If Walmart grows continuously, so that formula, at a rate of 6%, how much will Walmart be worth 2 years from now? What am I trying to find? M, P, R, or T? M. I'm looking for a dollar amount after some time has passed. So we're looking for the maturity value. What's my principal? Perfect. Because principal is the dollar amount before some time has passed. And then I multiply principal times E raised to the power R times T. This time R is 6%, which is 0.06. And then what is T? 2 years. On your calculator, props to the people who brought it today, but look at your calculator and you have a button that says second, and you've got a button that says LN. You want to hit the second button and then the LN button, and that's going to give you e to the x. So if you're wondering how do I calculate with Euler's number, you type in 697.52 times second ln 0.06 times 2 close parentheses. And what is the maturity value I get? It's like 786.45 billion. So you would use this formula anytime something is growing continuously. You might say that Walmart as a business grows continuously because they sort of operate 24 hours a day. So it doesn't make sense to discretize it. Now, really briefly, there are different types of personal debt. We already said credit card debt is typically about 20% interest rate, compounded monthly. There are also a such thing as personal loans, which means you just go to the bank because you need money for one thing or another, and they'll lend you money, typically at a rate of 8 to 10%. There's a little bit of variation here because it depends on your credit score. If you've got a really good credit score, you get lower interest rates. If you have a bad credit score, you get higher interest rates. A car loan, like if you go to the dealership and you say, I want to buy a car, but I can't pay for the whole thing in cash right now, they'll allow you to make a car payment, but they will charge you interest as you're making your car payments before you've paid off your car. And so you might have a similar situation where they charge you 8 to 10% interest. For a student loan, it depends. If your student loan is not federally subsidized, you might have to pay 8 to 10% interest. If it is subsidized by the federal government, like you do the FAFSA, the FAFSA, then it's like 6.5%. Home mortgages have a lot of variety. I got really lucky, and I happened to be buying a house when interest rates were like 2.3%, which is really, really good historically. But I think nowadays they're more like 6.5%, maybe even 7%. Interest rates aren't so great right now. So there's a lot of variety with your mortgage interest rate. That mostly depends on what the Federal Reserve has set their interest rate at. And right now interest rates are higher than they used to be a few years ago. So there's some variety here. Mortgage interest rates are always going to be lower than any other kind of personal debt. Do you know why? Your interest rate for your mortgage is going to be lower because you have collateral. if you fail to pay your mortgage, the bank will take your home from you. They will repossess your house, and they will call it a foreclosure, and they'll resell it to somebody else. They take all the money, and it's a way for a bank to get their money back. So the bank isn't really taking very much of a risk if they loan me money for a house, because if I ever quit paying them, they'll just take my house and resell it, and they'll get their money back. So they're willing to offer me a low interest rate if I put up my house as collateral. They're not really taking a risk, so they don't have to make a lot of money off of it. On the other hand, if I am borrowing money in the form of credit card debt, they are taking a big risk. Because I could run up a lot of money in credit card debt and then just declare bankruptcy and have my credit card debt absolved, and the bank has no way to get their money back. They just lost that money. So they're taking a really big risk if they offer me credit card debt, and that's why they have to charge me more money for that kind of loan. Car loans are just about as bad as personal loans because cars aren't very good collateral. And like, make no mistake, if you don't make your car payment, the bank will send a repo man to steal your car from you. But when the bank resells your car, they're not going to get back the full amount for it, right? Cars depreciate really fast. You drive the car off the lot, it loses half its value. And so the bank is still taking a risk for car loans. So you get higher interest rates if the bank is taking a higher risk. And if there's banks taking less risk, they'll offer you a lower interest rate. Same deal with credit scores. If you have a great credit score, the bank thinks it's a less of a risk. It's less risky to loan money to somebody who has a good credit score. A good credit score is supposed to mean that you're more likely to pay your money back. But you can also personally make investments, right? I had a crazy aunt who lived in San Francisco, and every time we would visit her, she would give her nieces and nephews money, and she would just open up her freezer, and she had like one frozen pizza box, and she would just pull out rolls of cash, and she would hand us money. If you just store all of your cash in your freezer, you don't make any money, right? That's a 0% investment.
Actually, you're losing.
If you take your money to a bank and get a CD, which is a certificate of deposit, then you can at least make some money. And this is, I've seen, a few years ago when interest rates were lower, some CDs only offered like 0.1%, which is very, very bad as an investment interest rate. But nowadays, interest rates are higher, and so you might see a CD advertised for like 4.5% if you find a good CD at a bank. You could also buy savings bonds from the U.S. government. So the United States is in debt. Our government's like $30 trillion in debt. Whenever the U.S. government wants to borrow money, they could borrow money from other countries, right? Or I buy up U.S. savings bonds. And so in a way, the United States government has taken a loan from me. I've loaned the U.S. government money. I've purchased savings bonds. And so they're paying me back interest on these savings bonds. And the interest is normally like, 3% to 7% on savings bonds. You can buy those at treasury.gov if you're interested. If I wanted to buy a stock market ETF, an exchange traded fund, these long term are expected to make about 7% interest. And we'll talk more about that here in a second. And what if I just say I want to buy a particular stock? Like I really like the company Amazon, so I want to buy just stock in Amazon. This has maybe the most variation of all, because you could lose all of your money. Right? If you had bought Amazon stock in like 2003, Amazon was growing really, really fast as a company. Maybe you're making 30% interest year over year on that investment. On the other hand, if you buy stock in a company that you think is great, and then the next year they go bankrupt, then you've lost all of your money, right? It's an extremely risky thing. And so the trend is, once again, the more risk you're willing to accept, the higher returns you can get. But if you want something that's low risk, you typically make less interest on it. A CD from a bank is very low risk. You will not lose all of your money by getting a CD from Chase or whatever. But they're also not going to offer you a very high interest rate. Savings bonds are also very, very low risk, right? Like if the United States government defaults on their debt, then we've got a lot bigger problems than just losing my money, right? It's one of those things where I consider it to be a perfectly safe investment. Buying a stock market ETF is pretty safe in the long term, but there is some variability from year to year. And so you have a higher interest rate with a higher level of risk. And like I said, if you want to accept a lot of risk, then maybe you could do better by betting on a particular company, but then you're getting into the realm of like gambling more so than responsible investing. But more risk, higher interest rate. Let's also talk about compounding frequency. So if you go and purchase a government bond for $500 today and it earns 6% interest, you might ask, how much is my government bond going to be worth in 40 years if I compound annually? If I compound annually, that means n is equal to 1. It compounds once per year. And that would result in $5,142.86 at that rate for 40 years. The word semi-annually means half of a year. Like semicircle means half of a circle. And so if it compounds semi-annually, it compounds every 6 months, and n is equal to 2. It compounds twice per year. And if I compound twice per year, you'll notice that the maturity value is just a little bit higher. What if it compounds monthly? Then n is equal to 12. And the maturity value is just a little bit higher. What if it compounds weekly? Then n is equal to 52 weeks in a year. What if it compounds daily? Then n is 365, so there's 365 days in a year. And then lastly, if we're compounding continuously, then we use a completely different formula. And what I want you to notice is this. As I'm increasing the frequency, does the maturity value go up or down? It goes up. If you compound your interest more frequently, then the maturity value grows more. It grows faster. But there's kind of diminishing returns on this, right? Like going from annually to semi-annually makes you, I don't know, like almost $200 more over the course of 40 years. You go from semi-annually to monthly, it's another $150 over the course of 40 years. But it drops off. Like going from monthly to weekly only gets you an extra $21, and then weekly to daily only gets you an extra $7. Going from compounding once per day to compounding every single second of the whole day continuously only gets you $1.09. So, I may have said this already. Every single credit card, every single car payment, every single mortgage payment, everything you almost ever do is going to compound your interest monthly, because it's a way for them to squeeze more money out of you than if they just compounded annually, right? They get more money from you. But a bank doesn't want to sit and calculate your interest daily. So as a compromise between amount of effort they have to put in and the amount of money they want to get out, your bank is going to compound your interest monthly. If you are buying U.S. Treasury bonds, they actually compound those bonds semi-annually. But that makes sense because the government doesn't want to pay you more interest, right? They want to pay you less interest, and so they're willing to compound less frequently. Anyways. So the more frequently you compound, the faster the maturity value grows. This is a little graph where the bottom stair step curve, this is 1 time per year. Compounding the same interest rate as these other two curves, but this one, you'll notice, is monthly. There's 12 times per year where the interest is compounded. So this is like 1 time per month. And the last curve on top looks smooth, but it's not. This is actually what it looks like to compound 1 time per day. And so there's a big difference at the end of 5 years between annual and monthly. But there's only a very little difference at the end of 5 years between monthly and daily. So most everything is done by the month. Here's question number 2, finally. Consider an interest rate of 5% compounded continuously. If I see the word continuous, I immediately write down this formula. And 5% means 0.05 is my R value. But this question is saying, what interest rate, call that lowercase r, would provide the same return when compounding annually? And if I see compounding annually, well, then I would want to write down this formula. And annually means once per year, and so I might write down this. If I want the same return, that means I want the same maturity value. Okay? You see the word return, that means the same thing as maturity value. So what I'm going to do is set this maturity value equal to this maturity value. And this is p times 1 plus r to the power t. And this one is p times e to the power 0.05t. If I want to solve for r, I could divide by p. So let's divide both sides by p. And then I'm going to do something a little bit special to the left side of the equation. And that is one of my properties of exponents. There's a property of exponents that I called the power rule on your little handout. And it says if I've got e raised to some power parentheses raised to another power, I could just multiply the two numbers and then I would get 0.05t. So now I look at this equation and I think, well, I could continue to try to solve for r if I can get rid of this t power. And I could get rid of that t power if I just take the tth root of both sides. Now that root cancels with that power, and that root cancels with that power. I did the same thing to both sides of my equation. And so I get e raised to the power 0.05 is equal to 1 plus r. And that means r is going to be equal to e to the power 0.05 minus 1. So somebody who brought their calculator today, please indulge me and tell me what is e raised to the power 0.05, then minus 1. Yep. And if your answer choices are listed in percents, you might write 5.13%. That means the same thing. And let's remind ourselves what the question was asking in the first place. The question was asking, if I have an interest rate of 5% compounding continuously, Well, I know compounding continuously is going to grow faster than compounding annually. But if I wanted to make this compounding annually, what's the interest rate I could choose to make it grow at the same rate? And since annually would normally grow slower, I have to boost the interest rate just a little bit on the annual calculation to make it match 5% continuously. In other words, 5% continuous is the same thing as 5.13% compounded annually. So there's a difference, but it's not a huge difference. It's just a little different. In exercise number 3, it asks, if you purchased Alphabet stock for $100, then sold that stock 4 years later for $190, what was the average interest rate? Assume continuous growth. Okay, I see the word continuous, so I'm writing down this formula. The question is asking for M, P, R, or T. R. My question is asking me for R. So everything else should be given. What is my maturity value?
$190.
Yeah, that's the dollar amount after some time has passed, so it's 190. What's the principal? 100. What is T? 4 years. So I can solve for R if I just divide both sides by 100. And how do I get rid of the exponent base e? To get rid of an exponent base e, I have to use the logarithm base e. And the logarithm with base e is the natural logarithm. 190 divided by 100 is 1.9, and I find out that my interest rate, R, is going to be the natural log of 1.9 divided by 4. So what is R? Yep. 0.16, which is the same thing as 16%. Yeah, so remember, if I'm solving an equation, solving an exponential equation like this one, and I want to get rid of an exponent base e, I have to use the logarithm base e, because that's the inverse function. And the logarithm with base e is called the natural logarithm. Okay. Now, I said this earlier. I said if you happen to get a stock market ETF, which is an exchange traded fund, then you can expect a long-term growth rate of about 7%. VOO is an acronym. It's the New York Stock Exchange stock ticker symbol for a bank called Vanguard that operates an S&P 500 index fund, which you might also call an ETF. ETF is an acronym for Exchange Traded Fund, and ETFs are a good thing. In the old days, if we were like living in the 1940s, if you wanted to buy and sell stock, you would get on the telephone and you would call your stockbroker in New York and you would say, hey, I would like to purchase some, I don't know, what's a company that was around in the 40s? Some General Mills stock. And your stockbroker would walk into the stock exchange and talk to some people and like make it happen, negotiate a price, blah, blah, blah. But today, since the stock market takes place on just a bunch of computer servers, we have what are called ETFs. And ETFs is just a computer program that executes the purchasing and selling and price negotiations for you. What it means to be an S&P 500 ETF is this. The S&P 500 is a list of the 500 largest publicly traded companies in the United States that are listed on the New York Stock Exchange. So any big company where you can think of their name is probably on the S&P 500 list, like ExxonMobil, Chevron, Walmart, Target, Google, Apple, Microsoft, Ford, General Motors, Tesla. All of these companies are listed on the S&P 500. So if I get on my phone real quick and I pull up my little investing app and I buy $100 of VOO, then the bank, Vanguard, is going to take my $100 and they're going to buy 20 cents worth of ExxonMobil and 20 cents worth of Apple and 20 cents worth of Google and 20 cents worth of Tesla and 20 cents worth of Target and 20 cents worth of Amazon and 20 cents worth of Walmart and so on. And they're going to do that for me, so I don't have to spend the next 2 or 3 days making 500 different tiny purchases. The computer does it. That's what an ETF is. And again, the reason I want to do this is because if I just put $100 in one company, that company might go bankrupt and lose all my money. Or maybe not that severe, but they might lose value one day to the next. And if I instead buy stock in 500 different companies, one company does poorly, but the other 499 companies might do okay, and then it balances out, and on the whole, I'm still earning money. So we call this getting a diverse portfolio of stocks. And this is one way to do it, where it's super easy. The computer does it for you. I don't have to think about it. It just splits my money up between 500 different companies, and I don't have to worry about it. Now, I told you 7% is the rate you should expect. I'll show you how I came up with that number. What you do is you say, and I can see what the trends are. And for VOO, there's ups and downs, right? If you had bought VOO in November of 2021 and then you sold it in September of 2022, you would have lost money. That's what I mean by ups and downs. That's what I mean by risk. You can legitimately lose money by buying and selling these funds. But in general, I think everybody would agree that this is mostly an increasing function from left to right. So that's kind of the long-term picture, is that if you just are patient and you're willing to hold on to this for long enough, it will eventually go up. This right here is March of 2020. Do you know what happened in March of 2020? Yeah, the COVID outbreak in the United States. So understandably, there was a dip. But if you were just patient long enough to hold on to it, until March of 1 year later, then you would have been good again. You would have still made money. It's just about being patient and outlasting the little dips. Okay, still, you can download this data. And I've got a little Excel spreadsheet where I downloaded the data. And I'll point out 2 numbers from this list. The first is that in January 1st of 1994, the price of a share of VOO was $46.59. So in 1994, January 1st, $46.59. The other number I want to point out to you is, if we fast forward in time, January 1st of 2019 was $249.92. Now, let's pretend that this calculation is going to be compounded annually. I could say continuously or daily or whatever, but it just makes a tiny, tiny little difference in the interest rate. It's not anything practical. And so if we're compounding annually, I can write down this formula because n is equal to 1. What would you say if I'm trying to calculate what is R? What is the average interest rate? What would you say is M, my maturity value?
249.
Okay. And P, my principal?
46.59.
46.59. And then T is
25.
25 years. So let's rearrange this equation. I'm going to start by dividing by $46.59. That gets rid of the 46.59 on the right side of my equation. And then the right side of this equation is going to be 1 plus r raised to the power 25. And if I want to get rid of that 25th power, I would need to take the 25th root of both sides of my equation. And you might remember that the 25th root is the same thing as 1 divided by 25 power. And so if I want a nice formula for r, if I want to calculate my interest rate r in my calculator, I would do this. I would type in open parentheses $249.92 divided by $46.59, close parentheses, raised to the power 1 divided by 25, close parentheses, minus 1. Let me tell me what that number is. Yeah, 694 maybe? I don't remember the exact number, but something like this. And so in casual conversation, somebody might say that's pretty close to 7%. So we normally say the expected long-term growth rate. If you do your calculation on an annual compounding basis, you can expect 7% per year from a good stock market ETF. So I used the years 1994 to 2019 because it's 25 years, pretty long-term chunk of time. I wanted to exclude 2020 just because it's COVID and it was weird, and then Russia invaded Ukraine and that was weird, and then inflation's been unusually high, probably because Russia invaded Ukraine and all of that kind of stuff. But during a relatively normal period of modern history, we calculate a long-term growth rate of about 7%. In blue, I actually plotted all of the January 1st share prices of VOO. In orange, that's what it would look like if it grew exactly 7% every year. And so starting off, you can see, well, it grows a lot faster than 7% to begin, but then there's also some years where you lose money, or you lose value. And then it grows again a little bit faster than 7%, but then there's another year where you lose some money. And so it's ups and downs, but over the long term, we expect something like the orange trend to prevail after some decades have passed. So we've got some more question types, like number 4 says, suppose you just checked your investing account and you find that you have $6,000. You invested your money 12 years ago at a rate of 7% interest, compounded annually. Ooh. As soon as I see the words compounded annually, I'm going to write down this equation. Annually means n equals 1. How much money did you invest? So what am I trying to find in this problem? MP, R, N, or T? P. P is the amount that I initially invested. And so let's try to find P, and everything else should be given to us. Like, what is my maturity value? 6,000. What's my little lowercase r?
0.07.
0.07. N is equal to 1, and t is 12. So if I want to find p, I just take both sides of my equation, and I divide by 1 plus 0.07 raised to the power 12. Or, if you're in your calculator right now, you do 6,000 divided by 1.07 raised to the power 12. So what was that principle? What's the answer? Mm-hmm. Yeah, something like 2,664, 65, something around there. Very good.
Would you have to put it in parentheses on your calculator or no? The 1 point.
If you leave it as 1 plus 0.07, then yeah, you need the parentheses. But if you just write 1.07, you don't need the parentheses. Good question. I guess when in doubt, use the parentheses because it can't hurt. It definitely can't hurt you. Suppose you start a CD at your bank today with $1,000. The bank offers you 4% interest compounded monthly. Ooh, I see the words compounded monthly. I automatically write down my compound interest formula. Monthly means n equals 12. 12 months in a year. Okay, what is the question asking for? NPR or T? T. Yeah, it's asking how much time will pass. And so I know I'm looking for T. What is my maturity value? 1,500. What is my principal? 1,000. What is my interest rate? 0.04. Okay, let's start trying to solve for t. I'm going to divide both sides by 1,000. And this is what I get after I divide both sides by 1,000. Here's what we do next. We are trying to solve an exponential equation where my variable I'm trying to solve for, it's in the exponent. If this happens to you, you can solve it by taking the natural logarithm of both sides. So take the natural logarithm of the left side, and then take the natural logarithm of the right side. This is going to allow us to use properties of logarithms number 8. So remember that handout I told you to memorize? Number 8 on that handout says the power rule for logarithms is if I've got a power on the inside of my logarithm, I can take it out. And I'll just multiply this logarithm times 12t. So I've got 12 times t times natural log of 1 plus 0.04 over 12. Right. That's just a property of logarithms you have to know. And finally, to solve for t, I take both sides and I divide by 12, and I also divide by natural log of 1 plus 0.04 over 12, close parentheses. In fact, I'll tell you how to put this in your calculator. You type in natural log of 1.5 divided by, open parentheses, 12 times natural log of 1 plus 0.04 divided by 12 close parentheses, close parentheses. And getting the parentheses right really does matter, because if you just typed in divided by 12 without the little open parentheses there, then it's not going to give you the right answer. It'll divide by 12, but then it'll try to multiply times that natural log instead of dividing by that natural log. So that's important. Let me know when you're done, and you can tell me how many years this is. 10 point what? 15? 10.15? Cool. So if you get a 4% interest on your CD at a bank and you put in $1,000 and you wait very patiently for 10.15 years, then you can have $1,500. $500 free dollars. We've got just a few more left. If you make a purchase with a credit card today for any amount, and you choose not to make any payments, how long will it take for your debt to double? Assume 20% interest compounded monthly. Okay, when I see compounded monthly, I immediately write down this formula. And of course, monthly means n is equal to 12. So 20% is 0.2. Obviously, I'm looking for t. The question asks, how long will it take? So I'm looking for t. I'm looking for the number of years that are going to pass here. The only thing that's not given to me is what is my maturity value and what's my principal.
Can't you do like a hypothetical 100, 200?
Yeah, you could do that. That's true. That's a great idea. You could just say, well, any amount, I could just plug in 100 and then double that would be 200, right? And it doesn't matter what number you plug in, as long as this is 2 times as much, okay? In fact, you might even say that whatever the maturity value is, what I know is that it's 2 times the principal. So just so you know, this absolutely would work, just plugging in 200 and 100. That would work. You could also just say, well, my maturity value is 2 times the principal, and then divide both sides of this equation by p, and you would get this. Same thing as if you took 200 divided by 100, you just get 2 on the left side. But it works. Very good. And lastly, to solve for t, what would I have to do?
Oh, natural log.
Yeah, my unknown variable is in the exponent, so take the natural log of both sides of this equation. And then on the left side, I get natural log of 2. On the right side, I would get 12t times natural log of 1 plus 0.2 over 12. I already did the fancy power rule for logarithms. If you've got a power on the inside of the logarithm, you take it out, you multiply the logarithm by 12t in this case. And then t is going to be equal to natural log of 2 divided by 12 times natural log of 1 plus 0.2 over 12. That looks similar to what we did in a previous question. But I'm curious if anybody can tell me really quickly, how many years have to pass before the debt doubles on an unpaid credit card bill? You said 3.4? 3.49? Yeah, so about 3.5 years. That seems about right. So at 20% interest, it will double in 3.5 years. All right. You probably have heard this word before. And you probably realized that, like, if you could get into a time machine and rewind the clock 40 years and end up in, like, 1984, things were a lot cheaper then. You'd probably be shocked at how cheap you could get a loaf of bread and a gallon of milk and a carton of eggs and that kind of thing back in the 80s. In fact, there's lots of signs that you can find on eBay and stuff that are like old Coca-Cola ads where it's like, Coca-Cola, always 5 cents. And like today, that's like, I don't know, $1 for a Coke. This is called inflation. Over time, any currency is going to lose its buying power. The United States has the Federal Reserve. No, Federal Reserve sets the interest rates. The Department of the Treasury kind of gets to set what they want the rate of inflation to be. And they have always tried to target 2% in recent decades. The United States wants 2% inflation. Ideally, because the United States government has $30 trillion worth of debt, they would want the inflation rate to go up as fast as possible. Because if your currency loses value, suddenly $30 trillion of debt is not all that much, right? You know, if your currency loses half of its value, then 30 trillion is the same thing in value, intrinsic value, as like 15 trillion. Anyways, you don't want inflation to go up too fast because then you destabilize your economy and then people go nuts, like in Venezuela, right? They have like ridiculously fast inflation because of bad policy, and then there's a coup, and then just anarchy after that.
We're at 5% right now.
Yeah, so inflation has not been 2% over the past few years. Anytime there's like wars and other geopolitical nonsense going on, you can't always trust the 2%. But if you looked at the years 2012, 2013, 2014, 2015, 2016, 2017, 2018, 2019, you would see the inflation rate was 2%, 2%, 2%, 1.95%, 2%, 2%, 2.05%. You know, it's like really close there. But regardless, so money loses value over time. I remember when I was a kid, you could go to Rosa's on a Tuesday and get like a huge dinner plate for like $2.50, and you can't anymore. It's like $9. If you have an investment that's growing at a rate of 7% per year, but the United States dollar, which your investment is measured by, is losing value at a rate of 2% per year, how quickly is the intrinsic value of what your investment could buy in terms of bread and milk and eggs, how quickly is that growing? 5%. And so if you're going to do some long-term personal finance planning, you should maybe take this into account and say, yeah, I'm expecting the dollar amount of my investment to grow at 7%, but what that means for me practically in today's dollars is that it's going to grow 5% in value over time. And so that's not a bad number to remember. Inflation-adjusted value growth. And, you know, sometimes I think to myself, I would love to retire and not work at all, not have any income, but just, you know, live my life and live it only off the interest earned by my investments. That would be nice. Imagine I have a lifestyle of $85,000 per year. So I've got to pay for health insurance, I've got to pay my doctors, I've got to pay my dentist and my eye doctor, I've got to pay my mortgage, I've got to pay my property tax, I've got to pay my home insurance, I've got to pay my car insurance and save for a new car and pay for gasoline and restaurants and groceries and my cell phone bill and my Netflix bill and everything else. Maybe I want to travel and have some extravagant vacations in there somewhere. Maybe that's $85,000 per year. Imagine I want to save up some large amount of money, my principal, times 5%, because I could make 5% interest off of this investment every year. And then I'll just withdraw the just the interest I made. every year I'll just withdraw the interest I made that year, right? So it should be 5% of my principal. I want this to be equal to $85,000 a year so I can support my lavish lifestyle. The amount of money that I need to do this and retire and just live indefinitely off of this interest without ever losing money, only living my life off of interest, would be 85,000 divided by 0.05. You can put that in your calculator if you want. This is $1.7 million. So man, if I only had $1.7 million, I wouldn't need to come to work, right? I could just stay at home and withdraw my interest and live the high life. Be nice. So if you were retirement planning, this might be the first number they tell you about, is like, yeah, you should maybe try to reach $1.7 million by the time you want to retire. For some people that might be 70 years old or 65 years old or 60 years old, 55 years old, whatever. You should have to aim to get to this value at that point. The next question, if you were planning for retirement, is you say, I want to have 1.7 million saved up by the time I'm 65. And this is a silly question, but how much money would I need to invest in one lump sum at age 20? Well, no, I got my P's and my M's mixed up. My maturity value is equal to my principal times 1 plus interest rate raised to the power t. We're just going to assume compounded annually for ease of calculation. I want the maturity value to be 1.7 million, and I'm finding my principal. 45 years are going to pass, and so what is $1.7 million divided by 1.05 raised to the power 45? I actually don't know this number, so I need somebody to put this in your calculator and tell me. You said 89,000? Oh, 189. Okay. Okay, so if only I were a 20-year-old with $189,200, because then I could put it in an investment, and I couldn't retire immediately, right? I would still have to provide for my means for the next 45 years. But as long as I didn't touch that big old investment that's cooking in the background, it would grow on its own over time to 1.7 million, or even more, but in today's dollars, 1.7 million worth of value at age 65, and I wouldn't have to prepare for my retirement. That's not how most people work. Most people don't invest all their money in one lump sum, and if you consider that, then the calculation gets to be more complicated. What you could do instead is you could go online and use the tools available to us, and you say, I want Dave Ramsey investment calculator. Something you can Google search. And Dave Ramsey investment calculator is a website that looks like this. And you say, okay, my current age is 23 years old. I'm going to retire at 67. I don't have any money in investments, but I'm willing to contribute $200 a month. This last box asks you what your annual return is going to be. I told you 7% is good for a stock market ETF, so I always use the number 7. The website says 10 to 12%, but that is wrong. I showed you today, that's wrong. That's way too optimistic for a number, in my opinion. So I think we should use the number 7, and then we'll hit calculate. So the cool thing about this little calculator is it'll tell you, if you can just put away $200 a month starting at age 23, then by the time you're 67, this is going to grow to $705,000, which is a little bit short of my goal, but also look at this. I only personally had to contribute $105,000, which is a lot of money, but you know, spread over the course of 40-something years, 44 years. And actually, the growth from the interest is the lion's share of the thing. It's 85% of my total is not money that I worked for, not money that I took out of my own wallet and put in, but that's just interest. This is how my investment happened to grow over time. So that's pretty cool. And then to actually find what amount of money do I need to contribute monthly to get to my goal of 1.7 million, I just have to keep fiddling around with this until I find the right number, right? You can make it an iterative process where you just type in different numbers, like, yeah, it's about $500 a month, I guess. It's easier to save for retirement the earlier you start, right? Like, you can't ever start too early. If you start when you're 23, maybe you contribute $500 a month towards your retirement, and you can end up with 1.7 million. But what if you don't start when you're 23? What if you say, I'm going to wait until I'm 55 years old, when my kids are grown up and they're all out of college and I don't have any expenses, then maybe I'll start thinking about it. Ooh. If I were to wait until I'm 55 years old, now my personal contributions, the money that I had to work for, makes up 64% of the total. And the money doesn't have as much time to grow. So it only makes up 36% of the total. If you put in the money early, it has more time to grow and